Greetings and welcome back. Kamal here, the integral guy on YouTube, with yet another very interesting differential equation today. Let's see what we have. We have y equal to xy prime plus the square root of y prime squared plus 1. So it's a pretty interesting nonlinear differential equation, and it's actually an example of a class of differential equations called, I hope I'm not going to butcher this guy's name, Clairaut's equations. Correct me if my pronunciation is wrong in the comment section. Thank you. Where the general form is y equal to xy prime plus f of y prime, where f is a continuously differentiable function and Clairaut is dead. So how exactly am I going to approach this particular equation? It's a really cool one, not only in terms of structure, but also in terms of the solution development and final result. It's extremely pleasing. But how do I solve it? Well, notice that we have y expressed in terms of its first derivative, and this term here gives us some hope if we can expand it using the product rule for differentiation. So a hint could be to differentiate the whole thing one more time, and that would mean we would have y prime equal to, applying the product rule here, gives us y prime plus x times y double prime, and now we need the power rule, so that's 1/2, and here we would have root y prime squared plus 1, and upstairs, because of the chain rule, we have 2 times y prime y double prime, where we have some nice cancellation as well. And we have some even better cancellation taking place here. So this implies that we have xy double prime plus y prime y double prime divided by root y prime squared plus 1 equal to 0. And from here we can factor out y double prime and get x times, we have y double prime times x plus y prime divided by root y prime squared plus 1 equal to 0. This means that we either have y double prime equal to 0, or we have, wait a minute, much better, or we have x plus y prime divided by root y prime squared plus 1 equal to 0. Now this case here is pretty damn simple. Integrating gives us y prime equal to a constant of integration c. And recall that we had y expressed in terms of its first derivative. So if I plug in the value of y prime, I will get y equal to x times y prime. So that's cx plus root y prime squared c squared plus 1. So this is the general solution to our differential equation. Now, what about this thing here? Well, since we're interested in y prime, we could solve this equation for y prime in terms of x. So moving stuff around gives us y prime divided by root y prime squared plus 1 equal to negative x, which implies that, terribly sorry about that, y prime equals negative x times root y prime squared plus 1. Squaring everything gives us y prime squared equal to x squared times, let me just expand this, so we have y prime squared x squared, wait a minute, and yeah, much better, plus x squared. Now collecting all the y prime squared terms together, we have y prime squared minus x squared y prime squared equal to x squared, which implies that y prime squared equals x squared divided by 1 minus x squared, which means that we have y prime equal to plus or minus x divided by root 1 minus x squared. And this is a nice separable differential equation, which we can solve quite easily. So we have dy equal to plus or minus x divided by root 1 minus x squared dx. And integrating this gives us, on the left-hand side, we just have y, but on the right-hand side, we'll need a substitution that is letting x here equal to the sine of theta. And this implies that dx equals cosine theta d theta. And that means we have y equal to plus or minus the integral of x turning into sine theta dx turning into cosine theta d theta, and in the denominator we have root 1 minus sine square theta. Now, we know that root 1 minus sine square theta is cosine theta, so that means we have some cancellation, which implies that y here just equals plus or minus integral sine theta d theta. Now, the integral of sine theta is negative cosine theta, and we have the plus or minus signs here anyway, so this implies that y equals plus or minus cosine theta plus a constant of integration a. And now to return back to the x realm, recall that we let sine theta equal x. So this implies that cosine theta, which is of course root 1 minus sine squared theta, equals root 1 minus x squared. So finally, we have y equal to a plus or minus root 1 minus x squared, but we're not done just yet. We have a couple possibilities for the function y, and we have the corresponding possibilities for its derivative. And we already solved for a general solution, so let's take this information and plug it into our target equation and investigate the possibility of a singular solution. So first we're going to take y here equal to a plus root 1 minus x squared. And for our differential equation, that means the left-hand side, which is just y, is a plus root 1 minus x squared. And on the right, we have x times y prime, which in this case is negative x divided by root 1 minus x squared, plus the square root of y prime squared, which is, of course, going to be x squared divided by 1 minus x squared plus 1. So let's simplify the right-hand side now. So we have negative x squared divided by root 1 minus x squared, plus root x squared plus 1 minus x squared divided by 1 minus x squared, again some cancellation, meaning that we have negative x squared divided by root 1 minus x squared plus 1 divided by root 1 minus x squared. But wait a minute, that means we have 1 minus x squared divided by root 1 minus x squared, which of course equals root 1 minus x squared, so that's the right-hand side. But the left-hand side was a plus the very same thing, that is root 1 minus x squared, which implies that a here equals 0. And this is confirmed for the second case as well, that is y equal to a minus root 1 minus x squared. Okay, cool. This is actually very nice. This is incredibly nice because it implies that y equals plus or minus root 1 minus x squared. And what's so nice about this? Well, let me just square everything so that we get y squared equals 1 minus x squared, which implies that the singular solution to our differential equation is in fact the unit circle centered at the origin, which is very pleasing indeed. I hope you enjoyed the video. More importantly, I hope that you learned something from the video. Be sure to like and subscribe. Do drop me a follow on Instagram as well. And in case you like the job I'm doing, you think I'm doing some semblance of a good job here on YouTube, consider supporting my content on Patreon. All links in the description box. Thank you. See you next time.